So today I want to talk about building multi-agent RAG systems. One of the things I did about 20 years or so ago in my master's thesis, my project was on multi-agent software engineering, or MACE. And it's interesting that over a period of time, how software engineering has evolved from monolithic to then packages, object-oriented, and then to microservices. And we are now seeing this with AI. So if you combine retrieval-augmented generation with the same principles as MACE, then that's what we are going to talk about today. So I am calling it multi-agent RAG systems. That's my marketer in me. But hopefully it makes sense when you look at what we are going to talk. So last year, when, of course, the ChatGPT thing hit everybody as a wave, there were a lot of people who started talking about retrieval-augmented generation. And for those who don't know what retrieval-augmented generation is, it's basically giving the large language model context about your data, because an LLM is frozen in time in terms of data. And we were calling this in-context learning, but Meta came out with a paper that called it RAG. So we're going to talk about naive RAG, what it meant last year, what it means today, when it relates to enterprise data. Then we'll talk about what are the requirements for RAG, where is it headed when it comes to enterprise. And then we'll talk about the architecture of doing RAG, but with AI agents, and how some of the companies that we work with, they're utilizing it. And then we'll put it all together just to give you an example of a system that uses what I call as Mars. So let's get started with what exactly is naive RAG. So if you remember last year, if we go back to the base principles of retrieval-augmented generation, is that my data, which is all maybe unstructured, but the reality is you have structured and semi-structured and unstructured, then you would take that data, apply a transformer model to it, convert it into vectors or convert it into embeddings used interchangeably. Then you would match it back to the query that's coming in, and then you curate that data in real time, give it to a large language model, and then say, answer the question. So it's something as simple as, okay, you are a very smart prodigy child, but you don't have knowledge about the library of books I have. So when somebody says, what is Europa? Don't answer them with what you know about Europa. Let me go and give you context from my data, and I curate it, give it to the large language model, and then the LLM responds, oh, Europa is a project here, which is about something specific to that company. But when this started to happen, people really over-rotated on vectors and semantic search. And we can talk a lot about the semantic search and why vectors. But one of the reasons why it became really popular, because semantic search took a huge leap in 2022 with the transformers model. But when it comes to working with enterprise data, you're not really just dealing with unstructured data. You also have huge petabytes of data, like the companies that we talk to. They have literally 4 or 5 petabytes of data. And a lot of that is sitting inside of Snowflake. So that's structured data. Some of that is sitting in Mongo, that's semi-structured. And then a lot of data is coming in through streaming data. That could be Kafka. Now, when somebody starts to use a private ChatGPT against that data, first of all, you need to curate all of that data. So accuracy is a problem, because if you use text to SQL, that's still about 30 to 40%. So you probably have 16 pages long of SQL that you want your LLM to use. So there's a different methodology for that. But you also want relevancy. You don't want data that the large language model is giving you, which is even a few minutes old. So an example would be if I have a co-pilot for support, which is one of the things that we have built, and now certainly there's an incident happening in production, and somebody is asking an issue, something about the issue, and that bug has been fixed and other companies have already reported, you don't want that system to give you data from 2 minutes back when the issue was not fixed. So there are certain use cases where you want to combine real-time streaming data with your huge corpus of data and then provide that accurate result. So that's relevancy. And third, this is a huge shift because of large language models. We now see conversational UI becoming a big part of user interaction. And in conversational UI, you cannot wait for 3 or 4 seconds to respond. Because if you do, it's no longer natural. So a lot of companies that were doing analytics in over, let's say, hours or maybe even a few minutes and seconds, that no longer works because now you want to be able to do that in a few milliseconds. But you want to do it across petabytes of data. So how do we achieve this? Well, first and foremost, you want to look at the unstructured data. You want to look at the structured data. That's where SQL comes in. That's where your, maybe Mongo or JSON available data comes in. And then, of course, you want to look at events-based data, which is your streaming data. So an enterprise system actually consists of your file system data, which could be your PDFs. It also consists of JSON and document-based databases. So those could be coming in from your transactional systems. And then you also have lakehouses or warehouses or data lake. And today there's one big thing that has happened in the last few months is now the world is moving towards standardized Iceberg. So irrespective of whether you're using Databricks or you're using Snowflake, you can now standardize that data and not be locked into one vendor, but now you want to use it in real time. So you mix and match that Iceberg data with your transactional data to get real-time curation. And of course, you have SQL data. SQL, I know, is not a format, but that's what a lot of companies still use in order to do the BI and stuff. So this is a layer which we call as contextualization layer that will take data from the right-hand side, convert some of them to vector in real time, and the rest are still structured queries. You mix and match, you curate that data, you re-rank it, and then you give it to a large language model. But you want to do this in a few milliseconds. That's the big challenge. So this is where the shameless plug comes in. I work for SingleStore. So this is what we do. We started off our company known as MemSQL about 11 years ago. And MemSQL was in-memory SQL distributed database. And the reason why we changed our name was because we eventually got a patent for what we call as a single store for your transactional data, your analytics data, and it's a 3-tier storage. So it goes from in-memory to local disk to object storage, which in effect means when data comes into the platform, we store that copy as both in columnar format as well as in row-based. And because it's memory first, you can do transactions against it. And because we also store a copy in columnar data, you can run your aggregate queries, which is sum, average, group by, and all of that that you typically do in a data lakehouse, but in a few milliseconds. And it maintains asset compliance. So one of the things I tell people is, it sounds too good to be true, but it is. Go give it a try if you haven't tried it out. In fact, we recently did a trillion row challenge where we pumped in trillion rows of data and we ran analytics queries against it, which was orders of magnitude faster than, let's say, Mongo, Postgres, MySQL, and of course, other large databases used for analytics. So what makes it different is exactly what I talked about, the row-based, the columnar-based, and the last piece is hybrid search. So what does that mean? When it comes to looking for data, especially unstructured data, what typically tends to happen is you convert that unstructured data into smaller chunks, And this could be your images, it could be your text, or it could be audio and video. When you convert to vectors, that typically the search that you do is done through something called semantic search. And semantic search uses two primary methods there. One is called dot product, and the other one is called cosine similarity. So the way I explain semantic search is if I took a very large data set, broke those into chunks, then I literally calculate how that is stored in a space. So a dog and a husky and a canine, those are stored closer together. So now if I measure the distance between these objects, based on the distance, I know that a dog is the same as a husky or is very similar to canine versus, a cat and something else. So now when you do a dot product search or you do a cosine similarity, irrespective of that structured data, you can get a fairly accurate response back. But then what about the structured data? Because you still have 17 pages of SQL that people have optimized in the last 5-6 years to get a very specific response back. And in enterprises, you want to run that because you want explainability, you want row-level security, you want data governance, and you want auditability as well. You don't want the large language model to take an NLP and convert that to SQL and run arbitrary SQL against your database. So with that, what we are looking to do is you typically do that with an exact keyword search. And the big leader over there is the open source Lucene library. So now if I say, is there a word dog in the sentence, Huskies are from Alaska, the exact keyword search will say no. So you'll come back with a negative. But when you do a semantic search, it will say, yes, there is. So a hybrid search is when you do both a dot product and an exact keyword match, and then you re-rank the results in real time to give you the most specific answer. And that's hybrid search. So when you're working with a database, today almost all databases now, they have vector search. We had added vectors in 2017, so we have had customers that are in production with semantic search since 2017. We recently upgraded our Lucene search, so now you also have the same accuracy you would get in Lucene. What is interesting, though, is in the same query, you can run both the searches. So I can literally say, select whatever this column, do a dot product, group by, do an average, and then do an exact keyword search, and it gives me the result in like a few milliseconds. And the last piece is we recently added a Mongo compatibility layer. So if you have Mongo running, we call it Kai, you can literally change the connection string and you run a pipeline into SingleStore, and now the same find all or find one works exactly the same without any change in code, except that it's 88 times faster. Under the hood, the way it works, as I talked about earlier, is we make a fast commit into memory. Because it's a fast commit, even Kafka stream, which is coming in, you can start querying in like a few milliseconds. And then because we also store it as a columnar storage, you can immediately start running queries on it, and you can also start doing vector searches on it, because ultimately it all sits in one place. You can store it as a row base, you can store it as a columnar base. By default, we store it as both, but it's really up to you if you want to control which data goes in columnar and which data goes in memory row. And it's horizontally scalable, so we have aggregator nodes as well as leaf nodes, so you can literally scale it horizontally to as much as you want. And because the storage and the compute is separated, you can run very large jobs and then auto-scale it back to just one compute if you want to, after that load has passed over. So this is kind of the secret sauce. Now, when it comes to retrieval-augmented generation, obviously it is With enterprise data, you have a lot more requirements. What happens if somebody asks a query to say, who won the Olympics? And if I have a chatbot which is going against my data, I don't want to burn GPU by answering ChatGPT general questions. Similarly, if my chatbot returns data which probably the person is not entitled to see, I don't want that to go out. And then on top of that, I want auditability. I want explainability in the sense, why did you return this query? So a lot of that is managed through what is called input-output validation. So input-output validation literally is intercepting the user queries, and you do a few things with it. Either you see if this is the right query that we should respond to, or we don't. So that's input validation. And when the data does come out, so first of all, it's also cheaper and faster because at that point, you see that these queries have been asked quite a few times. You can use semantic search to then respond versus just responding saying, no, I cannot answer your query. So there are certain libraries right now which has really gained ground. Last year, when I started playing around, there was a library called Nemo Guardrails. And Nemo Guardrails is extremely good with this. It is now part of NVIDIA. So NVIDIA has these things called Nemo inferences or NVIDIA inferences service microservices or NIMs. And you can literally run those as a container on GPUs, and it runs extremely fast. But that's a separate microservice. So that's your input-output validation. Similarly, there's guardrails. Guardrails would be, I don't want anything that's either offensive or against the policy of the company to be able to go back to the user. So those are what guardrails are for. We talked about caching, but here the caching is not just last recently used, it's also around the nature of the queries that are coming in. If semantically they are similar, you want to then combine it, and as part of input-output validation, you also enrich that query. Say, hey, this user has a query which is similar to the 20,000 other users who ask similar query. So maybe you, and this is what perplexity does, maybe you put that as the next query and say, okay, you asked this query, most likely this is going to be your next query. Just click on that and you get the response. Hybrid search we talked about, and then we haven't talked about is re-ranking. So when you do these searches, a dot product is not an exact KNN search. What it gives you is a ranking between 0 to 1, with the 1 being the highest probability of that search result being similar to the query. And so what you could do is you can rely on that to re-rank and then give that feedback back to the user to say, this is the highest contextualized response. And then there are some libraries for that too. And then the last piece is you want to do evals or evaluation. If certain queries or result goes back to the end user and the user does a thumbs down that this was not really the right answer, you want to take that and then fine-tune the model or your entire pipeline in order to make it better. So it gets better over time. And that is called RLHF, or reinforcement learning with human feedback. And you can look at that audit data, or in real time, you do thumbs up and down, and then you push it back into the pipeline. Now imagine you're doing all of this, and you want that result to come back to the user in a few milliseconds. So there are a few things you could do here. One is you can put it all together. Let me see here. There's a little bit of a lag. So one is the monolithic piece, where you have the front end, the back end, and that's what it used to be in software engineering earlier. And then, of course, it became decentralized with microservices, Kubernetes, and so on. And that's the modular approach. The modular approach is, of course, much more scalable, but it also gives you independent control over how you release to production, so you're not changing or doing one change and then relying on your entire pipeline to be refreshed. So similarly, what we started to see last year was a lot of RAG, or retrieval-augmented generation, was happening in a monolithic way. You create an entire application that does input-output validation, it does guardrails, it does caching, and all of that, and it happens sequentially. Now, sequentially is okay for certain things, but when your enterprise RAG has become so more complicated and you still want milliseconds, you want to be able to do that in a parallelized fashion, and you want to maintain independence, control, scalability. So now we have this new architecture, which is around agents. There is an agent that manages the RAG pipeline, and that's the slightly older. It's funny how we say older, because a month ago this was something very popular. But you have multiple agents like a microservice, and there's a supervisory agent. So when you give the query, the supervisor agent will then break it into different tasks, send it to the different agents that does different things, aggregate and assimilate the result, and then send it back. But there's a problem with this. The problem with this is that the results are non-deterministic. If I give something to an agent and the agent decides to do certain things, it changes with every query. And as an enterprise, I cannot rely on that. So how do you make this into much more deterministic? But before we go to that, let's look at an agent. What is an agent? An agent, think of it as something that mimics a human in its cognitive architecture. Think of an agent as a microservice or an application, but it has three things. It has intelligence, which comes from its access to its own model. It has knowledge, so you can literally give it either SQL queries as functions, or you can give it access to APIs, and that's where the tools come in. Or you can literally give it the vectors specific to that domain. So now I have an agent that maybe is using a different fine-tuned model. It might be using an open source version, and it is all geared towards a specific job. And that specific job could be now related to one of the operations in RAG. So now we are getting into multi-agent RAG systems. But then if I want to now combine it in a multi-agent RAG systems, then I take all the principles that we talked about, which is a retriever agent. That could be SQL, as well as it could be a vector search. I could have an evals agent. That evals agent just does evaluations, it does re-ranking. I could have a structured retriever agent versus a vector retriever agent. And then I have a guardrails agent. Now, if I run each one of these using NIMs or something like that, and they're all running as a microservice, now I can really control the overall flow and the latency. But the biggest problem over here still a few months ago, that you would give it to a collaboration agent, and the collaboration agent will now start to give you non-deterministic results. So the way to solve that is through this notion called a graph. Now, with Llama Index and LangChain, or LangGraph, I should say, you can string together this entire workflow in a very modular way. So you create a graph. Within the graph, you create a node. The node could be an agent or a task. And then you have the edges. So you could literally say, with this query for this specific domain, I have this aggregator which needs to follow these steps very deterministically. It has if-then blocks, it has try and catch, and you manage the entire performance and accuracy within that graph. So that's the big difference over there. Now, how does it all come together? Well, here's an example. Let's pretend that we are building something like a Lyft or an Uber. And in that, what we want to be able to do is to take a very large, massive row or corpus of data of the rides that has happened, but I also want to take the real-time data and then I mix and match it to figure out which car goes to which person and so on. So we built this out using SingleStore and Snowflake. And the way it works, let's see if I'm still online, is so it uses geospatial data, it uses Kafka data, it uses Iceberg data, and it uses SQL data. Now what you're seeing over here is the rides and the riders and the drivers. So obviously this is simulated data. We are using Kafka to generate synthetic data to show it, but we are overlaying it. And then we are looking at this to say, all right, we have 58 people waiting for the pickup, the 196 rides happening in this locality, and these are the total number of drivers available. But what I can do is now use this to make real-time decisioning using AI. I can say, here are the total ride requests per hour, and as you can see, the refresh rate is 1 second, but the queries are coming back in a few milliseconds, and we are talking about, I believe, about 100 million rows of data plus Kafka coming in. So now I can use RAG to take all of this data, combine it with all the previous ride history data, and then we can make recommendation to say, looks like there's a concert going on over here, and you want to maybe send more drivers. And here, because of this pattern that we see, we think you should be able to do surge pricing. And you can do certain coupons for different users because maybe they're paying you $100 a year for an elevated level of service. So now all of this becomes possible and it comes back. You can see in terms of queries, but in the background, these are multiple agents that are working together in cohort to give you back the queries you need in order to make quick decisions. So with 2 minutes left, that's my presentation. Just to recap, we talked about multi-agent RAG or multi-agent retrieval-augmented generation. The entire problem being that if you want to do retrieval augmentation across structured and unstructured data, especially for enterprises, it has very different requirements. And if you want to do it across all kinds of data using different search, and you want to do this in a few milliseconds to feed the LLMs, then you need a different kind of architecture. And this is the one that we are seeing a lot now finally going into production. My name is Madhukar, and what I would also leave you with is if you want to get in touch, there are a couple of different ways. Don't believe anything that I said. Go try out the free version. You will be able to see the difference, I hope. And if you don't, send us an email. I monitor this email as well. And I'm more than happy to get on a call and show you this application that we built or some of the other ones that we have also built out. Thank you very much and enjoy the show.